is first, before that, because now you already have the topic. You already have the topic. So think about which topic you want to choose. Okay, and think about who will be your group mates. Each group contains 4 students. So you find your group mates. Okay, so because we have limited time, so we are not accepting like more than 10 topics. You have to form your group. And then think about it. So you have today and after class and too late and tomorrow. Okay, tomorrow you can discuss and through like WeChat, WhatsApp, whatever. And then you form the group and then you select the topic. I encourage you. So when you reply, just ask one student in your group to reply. Say, add a new discussion topic here. The subject, okay? So you can say topic whatever. You can just put your, say, if you want to pick topic 1. So and here you put your student, so name and so student name and number, because you will be a group, right? So here will be the student name number for 4 students. Okay, so and then here if you don't want bother, so if we here is a topic 1 already choose, and then you can even put your second option. It can be topic 1, so and then second option will be 3 or you'll be 5. Okay, like this one. Okay, so and then you add it to the forum, but pay attention. It's hard to say. Let me see. Yeah, it's still like say you probably keep an eye on it. So if you when you post to that, so refresh the whole page to see if someone already select topic 1. So and you do better not just leave it like this one, because like if someone already like mentions 3, so and even you say, for example, you say topic 1, your topic 1 has been you do that at 10:05, but your topic 1 already have been selected by some group like 10 a.m. sharp. Okay, and then so another group like at 10:05, so and so right after you select topic 3, and then so you lose to this one. So maybe not this one. Okay, so just your own topic, and if you see other groups select your topic, you should immediately so add another discussion 1, and then to post to a forum to claim this topic. Okay, so this is how you do that. Okay, so and anyway, so now we'll make it to be available so for access. So this Friday, 10 a.m. So only ask one representative from your group. So remember to include topic title you've chosen. Sorry, I didn't include, but you have to include topic title you've chosen, the name and student number of your team members in the post. So, and the title is assigned on a first come, first serve basis. Okay, then once the topic has been selected by other group, which is in front of you, and then so you have to choose another one. So, and if you see your preferred title already taken, so then select an alternative one. Then the forum open at 10 a.m. this Friday. And please choose your title on before so March 15th, because so next week in our class, I'm going to announce the selection, the final selection so of the title. So which students do which project, so which title, so I'm going to put that into a table, and then so we finalize that one. I'm going to upload so onto BU e-learning, and then you know about it. Okay, and then so for that presentation order, so because now we're having the online so lessons, so it's difficult to say to have some lucky draw to see which group present first. Then for this case, so we just like present by order. That means topic 1 will be the first one to give the presentation. Topic 2 will be the second one. Okay, so everything fine now? So understand? So any question about this group oral presentation? So about say how you choose the topic, how to reply, and then so what needs to be included. Everyone fine with it? Is that okay for you? Yeah. Okay. Thank you. Thanks for the reply. So. Okay, so now let's back to this one. Let me see for 1 minute. Wednesday's class is always so tiring. Yeah, it's too late. It's already 9. Let's see this one. Okay, so let's go. And then we finished that one. So here just summarize something of an analysis condition as function particle size. So just give you 2 tables. One is at constant column length. So the other is at constant efficiency. That means L unchanged. Here is N unchanged. So it's same as what we did the practice. You can see just now we just do this one. So when from 5 decreased to 1, what happened? So analysis time, you can see that. And then N, so pressure drop and flow rate, right? Okay, and also length the same. So, and this is N constant. Just now we did this practice, 5 to 1. So how does that influence? Because N is the same. So, and here's how influence signal to noise ratio. And then, so how about the L? So you can see that. So flow rate always increase 5 times. And pressure drop, so will be just like say 25 right times, not 125. And signal to noise ratio increase 5, right? And so on. So if just now you feel tired and didn't do that practice by yourself, and then so anyway, so this slide also provides these 2 tables for you to do. So when you are preparing for the exam for revision, so you can still use these 2 tables to see whether you got the correct answer or not. Okay, so where's this one? Okay, where's my, oops, sorry, my mouse. Okay. So this is example, furthermore example about, say this one, say constant N. So it just show you more about, so particle size change from 5 micrometer to 3.5 to 2 and to 1.7. So, and how that influence, so the time. And also you see they get same height, looks like same height, right? Okay, but actually, so here pay attention, they injected different, so different volume is actually, is the sensitivity actually increased, you know that. Okay, so and also the flow rate, so how the flow rate change and so on. So, and how about the influence on the resolution? Not changed because N is same, so that's why resolution is the same. And for this one is the analytical condition using that one. So this is using very common column format, because let's say here it shows the column ID for that one is 2.1 millimeter. And then so, and for this one, the if it's the DP is 5, and it takes about if it's like say 2.1 millimeter, 15 centimeter long. So if its DP is 5 micrometer, it takes about 18 minutes to do so. But to finish the run, and then so however, so when you're using the 1.7 micrometer, you can use a shorter column. So and 5, and say for example, so here if we want to get the similar N number, not just 5. That means like say when particle diameter decreased to 1.7, so you can using a shorter column, so and which is just 10 centimeter long to achieve about the same so column efficiency. By time, so and your analysis time dramatically decreased from 18 minutes to 4 minutes. Okay, and then however, so in this way, so the pressure drop has been increased so a lot, right? Okay, so this is for you to get more idea what is the reasonable, or what is the common condition, a little condition. So using a common column format. So assume that diameter, this one is 2.1 millimeter. So and different lengths, and then so the time required for analysis to achieve some reasonable column efficiency. Understand? Okay. Just later on. So if you in your real analysis, if you need this information. And because we keep talking about linear velocity mu, here it shows the mu. Okay. So and however, when we talk about flow rate, so it's milliliter. So that's why when you calculate that one, so you have to consider about the inner diameter of the column. We actually mentioned that, right? Okay, so how to convert that one? Convert from mu to millimeter. How to convert mu to milliliter? Okay, so from Q, okay, to the flow rate. So this one you have to pi. The time this one is actually pi r square. R square is this one. So this is inner diameter. Half of that will be inner radius, right? Times mu. And then so that will be this one. For this example, so now for its mu is 8 millimeter per second. Okay, so you can convert that to 0.8 centimeter per second. And then so, and this one is the inner diameter 1 millimeter. So that could be, so 0.5 millimeter for the radius, right? So it's 0.05 centimeter for the radius, and do the calculation, and then you can calculate. So the flow rate. Okay, so that means like, so for here, so the optimized is 4 millimeter per second. And if you're using 2.1 in the diameter one, so that is correspond to the flow rate is 0.6 milliliter per minute. 0.6 milliliter per minute. Okay, understand? So this is how that works. So when we talk about the packing material of the HPLC column, so you can see because now it has to handle even larger pressure, right? Okay, so you have to maintain the retention capacity similar to HPLC. So but you have to think about, probably you have to use some new material so that can stand such a high pressure. So because its pressure dropped, so increased a lot, right? So silica-based particles, they have good mechanical strength, but they suffer from several disadvantages. I think one we already mentioned is that pH limit, right? The pH limit. It has limited pH range. It cannot be too acidic or too basic, because when the pH value is greater than 8, so the silica can form soluble silicate species, so that causes the dissolution of the stationary phase. And then so if it's like, say, too acidic, if pH is less than 2, and then so, and also the it's kind of like, say, also dissolved hydrolysis, that one. So, and even the hydrolysis even happens in alkaline solution as well, alkaline condition as well. So, and that leads to degradation. So that's why. So silica based column always have this kind of problem. Okay. So, and polymeric column can overcome pH limitation, but they have some own issue, such as the limited capacity or low efficiency. So that's why for the UPLC, this one for the waters, so they have this one, the bridged ethane hybrid. Okay, so that means that they put the ethane group so into original silica column that packing. So they have this hybrid. You can see that. So this is silica packing column particle, right? Okay, now they put this methane group in between, called syn bridge, and you can see here. So this orange one. So in this silica matrix, and that's such a kind of improvement. So that one can greatly enhance the mechanical stability of the original silica matrix. Okay, and it can withstand not only high pressure, but also the high pH. So, and this is so that's why. So you can see, so that's why many of the UPLC column you buy, you call that BEH. Now you know what is BEH, bridged ethane hybrid. Okay, and that means ethane grip, then bridged, so in this silicon matrix. And then, so this is the, how to do that. So it has C8, C18. So reverse phase, C18, and then so this is a phenol group, this one. So, and different column. And this is a pH gradient separation with 5 micrometer column. So, and this is 5 micrometer. So you can see this is, or finish at 5 minutes. And it's a short column, So, but like say here, not really well separated. So here it looks like something as well. But if you see, if you're using so 1.7, you can get obviously narrow peak and more separation here. So, but it's a 5 minutes actually, you can get the same so resolution. So within shorter time. So because you can optimize flow rate 0.6 instead of just 0.2, right? Okay, so you can increase that flow rate, and then so you can achieve the separation within 1.7 minutes, and at the same time, so you can keep the same so resolution so as what you get for the 5-minute separation, right? Okay, and obviously you get narrow peak, then still not sacrifice the separation. And if we compare like 5 micrometer and 1.7 micrometer column, so and this overlay them. So let me see, and you can see that. So this is a signal, so it's much sharper and more sensitive. So, and you can see because the sensitivity increased. This one we already did the calculation before, so you all know that. And this is the continuous so injection. So how many of them? See, overlay of 7 injections. Okay, so looks like the same one, right? So it shows the mutation time reproducibility, so repeatability. So quite stable. And also, what on the top is the C18 column, and what here is the UPLC column. You can see before it has to use like about 40 minutes to finish run, but now you can do everything within 5 minutes. Excuse me. And here, so, and for the peak width, we switch to the UPLC column. So a narrow peak, right? Okay, so this is W, okay, narrow peak. Okay, so to summarize that, so the benefits of the UPLC is so clear. I think after we do this calculation, so that's why I derive that. I go through that together with you guys. So because then you will know clearly why we decrease DP can really increase the separation efficiency and resolution. So how did that achieved? Okay, so obviously you can see the benefit speed, so obvious, right? So obvious. So from 37.5 can go to 5 minutes. Okay, so speed much faster. If you fine with that, your original so resolution. So it can be when you decrease by 3 times, your time speed can be increased by 9 times, right? 9 times faster. So the samples can be analyzed faster. So and then so if your company have UPLC, and then so you can analyze more samples so per day, and then so you're more efficient, right? So you can get the data returned to the client faster. And then so also you can see the data is quite reliable and robust. We have very good repeatability. So no need to like to always say, I see the off of the retention time. Okay, this one has some ghost peak coming out, something then you have to verify that, and then that's another day. So that's why. So if you have very repeatable data and reliable results, so that also save your time to do the verification, right? So so you can use that one to solve some problems, and also the UPLC can be used in different forms. The normal elliptical column we introduced, but also can use for the microball column. So we mentioned a little bit 2 weeks ago, right? So in the lecture. And the column chemistry is that way. So the bridge ethane hybrid is the most quite popular right now. And then so for faster separation, you can use a column that's just like 5 centimeter long. So that is pretty enough. So, and use UPLC is now possible to take full advantage of chromatographic principle to run separations on shorter column, higher linear flow rate for increased speed, right? So this with better resolution and sensitivity that already mentioned all the parameters you guys, okay, previously so calculated, so derived. And UPLC begins to fulfill the promise of increased speed, resolution, and sensitivity predicted for liquid chromatography now. It's making better. And then so, and this is what we talk about so UPLC. So good. So we finish this topic. Now, oops. Ion chromatography. Are you guys tired? Yeah. Let's see. Nice ion chromatography. We come to this one. May not talk too much about it, okay? So I guess everybody must be very tired. So this is a very long lecture every Wednesday. So, oops. Okay. So, okay. So we just start a bit. Let's see, what time is it? Oh, we only have 10 minutes. How about we just fill it? Let me see. We just finish a few slides, okay, and let you guys go. It's timing. So, ion chromatography. So ion chromatography is also liquid chromatography. Okay, so it's share the similar configuration as HPL system. So you can see it has a pump, injector, detector, and data station. And if we talk about the chemical component part, it still have mobile phase and the stationary phase. But for ion chromatography, it depends on we're talking about ion exchange or ion exclusion. So, and if it's ion exchange, it's like, so SP column similar. So strong cation exchanger, strong ion exchanger, weak cation exchanger, weak ion exchanger, that one. So a high pressure pump also is required for ion chromatography. So to force the mobile phase to go through the column at the typical flow rate about 1 to 2 milliliter per minute. Okay. So, and however, one thing you have to pay attention is like, say, because for ion chromatography, we often use strong acid or strong base or high concentration salt as the eluent. So that's why for all the tubing, so you want to use non-metallic. You don't want to use joint tubing. This one, you want to use some PEEK. So you want to use different material. So because then if you're using with strong acid, strong base, so high concentration salt, that may corrode the metallic so tubing. So that's why I use PEEK. Okay. So and for the pump, using the dual piston gradient pump, and also because again, so later on we talk about the mobile phase. So the mobile phase, a typical mobile phase for ion chromatography can be sodium hydroxide. So this one, so we want to keep it so under 1/3 of atmosphere. We want to keep it under inert, so gas. Okay, so when under helium. Why? When you, especially when you're using a say a very alkaline solution, sodium hydroxide. The reason for that is because you want to prevent CO2 get in. Because when CO2 get in, so it becomes sodium hydroxide to sodium bicarbonate, right? Okay, or that one. So, and then what happened? So it's bicarbonate, and then so pH change, right? Okay, so and then so when we can use an ion chromatography to analyze not only say this one, so many things. So not only inorganic ions, but also organic ions, so organic acid. So for example, we can use ion chromatography to analyze ions in drinking water. So like chloride, nitrate, sulfate, and so on. So we're using that to even in processed water, what I mean. So, and we used to monitor the sewage treatment, right? Wastewater treatment to see that already removed nitrogen, and then so those kind of things. And cation ionize. So we also using, like my group, we're doing the PM2.5 analysis. We use this one to analyze the cation ionize in PM2.5. So we also use IC to analyze the fluoride in toothpaste, and then so the organic acids in beverage. But this one, so better using the ion exclusion chromatography, and then so and soil and fertilizer, the ions, so and so on. So when we're talking about the ions, so technique to they're able to separate the ions, including the ion change chromatography. This is the most popular one. So that's why we are focused on this one. We also talk a little about the ion pairing. Okay, but it's not not our focus. Okay, so the ion pairing are one. So this one is not the favorite one. And then so ion exclusion chromatography. So this is the one we often use to analyze the carboxylic acid. So for the carboxylic acid, organic acid, we're using the ion exclusion chromatography. For ions, if we want to separate different ions, later on we also mention for capillary electrophoresis, you can do that. So for ion exchange chromatography, IC, if you want to analyze so cation, you have using the column for cations. If you're using ionize, you have to use the separate column that used for ionize. You cannot do the separation of cations and ionize simultaneously. Okay, so they have their own column. But however, for capillary electrophoresis later on, I'll show you, it can separate both cations ionize at same time in the same run. Okay, so this is different. It's something interesting to know. Okay. And different mechanism. So when we talk about the ion exchange, that's quite straightforward. So first one, so like for this one, now the stationary phase is fixed ion. Okay, so that means the stationary phase is negative charge. So that means it will retain what? It will retain so positively charged analyte. So it's the cation exchanger. So, but before we do analysis, we always have the counter ion on that to protect the stationary phase, and put your sample in, and sample go through, and then to retained by the column. Okay, retained by the column, and then so this first one is the start condition that to get the counter ion in, and then load the sample. And now you load the sample, your sample will compete with the counter ion, and then we kick them off and then replace it, and your sample will be retained by the stationary phase. And then so you go through the eluent to have other content compete and elute the sample out, and then so regenerate for the next round. Okay, quite straightforward exchange. So everything based on, for ion exchange, based on electrostatic interaction. So for ion exchange, the principle is quite straightforward. So ionic analyte, they separate on cationic or anionic site of the stationary phase, depend on what is cation exchanger or ion exchanger. So they have column to support dynamically exchanged or permanently bonded ionic group, and the mobile phase is often an aqueous buffer solution. Okay, can be acid, so can be base, or can be a salt. Okay, so a salt one. So and then the migration rate of the ions really depends on the type and concentration of cation ions in the mobile phase. And then first one, rotation time based on the affinity of the ions. So for the ion exchange site, so that one's charge density, for example. So the charge density for that, and then for example, if you have the higher charge, multiple charge, 3 plus, stronger than 1 plus, right? Okay, so a smaller diameter, smaller radius, and you have higher charge density and stronger affinity to a stationary phase. And also this you can, for the elution, you can play with the ion strength, the salt concentration, and also the pH of the mobile phase to put the competition between the buffer ions and the ion to elute them out. Okay, so and when we talk about this one, so and ions, so monovalent, divalent, trivalent, that means the positive, single, one, so it's 2 plus and 3 plus. Okay, so like this one, or 3 minus, or not really plus, I just use an example. Okay, so for example, don't want to confuse you guys. So depending on our cation, and then for cation, including this one, so including the inorganic metals, so ammonium, so also including say inorganic, that's one, let me see, inorganic, organic amine. For organic amine, this one, it can be charged normally. So it can be charged normally when pH is less than 9. Okay, so and for ions, the inorganic quite straightforward. Those chloride, fluoride, sulfur, so nitrate, but also can be organic acids. So for organic acids, and for COH, really depends on. So the normally charged, so when pH is larger than 3, right? Okay, so and also can phenols, so that can be like higher, let's say. And also sometimes we can even say for amino acid, so amino acid, so they have positive charge, so when pH around about 2.2, so and or say they can be negative charge, so then when pH is higher than 9.4 or something like that. And for sugar compound, they also have that one, they also have this OH group, right? Okay, so and they can be charged, they can be negative, so at very basic condition when pH is larger than 12 or 13. So that is basically how we can divide them into different groups. Okay, so and probably we can start from slide 8 next week. Okay, so we start from the ion exclusive chromatography. So this one is particularly useful for the analysis of the organic acids. Okay, so and that's all for today. We already have enough, so we only have like 5 minutes break. So that's all for today. So I hope you guys okay. So with today's content. So yeah, do you have any question? You can ask. So will I help you to fill vacancy? Okay. So I understand. Do you guys have a WeChat group or WhatsApp group for? I guess you guys need to do some experiment before. Do you guys have those communication group? Because I'm not really can directly like say contact you guys. I only through email. So yeah, you have WeChat group, right? Okay. So can you guys like using like say WeChat group or okay for non-local students? I think a local student also have the WhatsApp group, right? So can any So full-time local student reply me. Do you guys have the WhatsApp group? So no, yeah, WhatsApp, yeah. So how about try that first? Okay, so if you only get 3 group mates, you write it down first. Okay, so if you anyway, you pick up the topic you like first, but do not do that. Say only yourself, and then you reply and take the topic. No, I don't encourage that. So, and it would be quite difficult to do the arrange. So later on, how about that? Okay, so try at least to find 2 or 3. So at least 2 group mates. That means including yourself. So 3 of you. So and do that. So, but if you really have difficulty, I will try to do that. But the only way I communicate with you guys is in class. So in this class, and then probably I can show the table to see so whether we can do some arrangement. Because yeah, face-to-face lecture is more convenient. So here we have to overcome many of the difficulties while doing everything online. But we have to, no option right now. Okay, so well, okay, so try to form the group. Yeah, so that's what I can do so far. Yeah, I can definitely help you later on. So, okay. Any other question? Any other question? If no question, so that's all for today. So bye guys. See you next week. Okay, bye bye. Thank you.